Okay, so in our next lesson, we're going to move from using some properties of exponents to talking about exponential functions. And we've only talked about one other type of function this year, and those were linear functions. So linear functions were functions where if you graph them, they were a line. Linear functions increased by addition, decreased by subtraction. So exponential functions are a little bit different because exponential functions increase by multiplication or they decrease by division. So the definition of an exponential function is that an exponential function is a function of this form, y equals a times b to the x power. Now when we write these functions, a and b are going to be numbers that change. X and y are going to be the variables that we write to represent inputs and outputs. So in these functions, a is never 0, b is almost never negative, and b will never be 1. And we're going to explain kind of why that is further in this lesson. So what I want you to understand in these functions, and we'll get to this eventually in the future, but when we talk about exponential functions, I talk about a as being what I call the starting value, and then b is called a growth or decay factor. And we will get into the specifics of that in the next lesson, but right now we are just focusing on what is an exponential function. So in example 1, we're just going to tell the difference between linear and exponential functions. So in part A, we look at a table, and basically what you're looking at is the pattern in this table, the change in the y values. Now, in general, x values are going to change by a consistent amount, meaning the x values are going to change by adding 1, 1, 2, 3. They might go up by 2s, 4s, 5s, but we're looking at the change in the y values. The y values in this function are changing by multiplying by a common factor. So multiplying by 3. That's repeated multiplication. So this function is an exponential function. So exponential functions change by multiplication or division. In part B, exponential function for part A, it changes by multiplication. So this, my handwriting's bad there, sorry about that. This function changes through multiplication. In part B, y equals 3 times x. This is a linear function. And the main reason this is a linear function is that x is not an exponent. That's really what you look for in an exponential function. Do you have a number being raised to the x power? Okay, 3 times x would be a linear function. So in the guided practice, just take a quick minute to pause the video and answer the question, are these linear or exponential? And be prepared to explain why these functions are linear or exponential. Okay, so A is linear, B is exponential. A is linear because it's changing by addition. If it were changing by subtraction, it would still be linear. Part B, it's exponential, and that's mainly because this is 3 times 6 to the x power. Now, I know I'm not giving very in-depth or long explanations why, but that's the main difference between a linear and an exponential function. So, in example 3 is mainly just you getting used to using a calculator to evaluate an exponential function. So this says, suppose 30 flower beetles are left undisturbed in a warehouse bin. The beetle population doubles each week. The function f of x equals 30 times 2 to the x power gives the population after x weeks. How many beetles will there be after 56 days? So in this function, the input x represents the number of weeks that have passed. So we're given 56 days. So x would really equal, if we're getting it in weeks, 56 days divided by 7 days a week, that would really be 8 weeks. So we don't just blindly plug in 56. We don't blindly substitute in 56. We are understanding that the input is supposed to be weeks, the right units. And it's extremely important here because that can throw off our math. So to evaluate this, x is 8. So I'm going to do f of 8, input 8, becomes 30 times 2 to the 8th power. And in your calculator, you would do 2 raised to the 8th power. Figure out what that is. That's 256. So this becomes 30 times 256 equals, then I will multiply 256 by 30. So that would be 7,680. And I want to write beetles. I want to have the right units when I finish this problem. So use order of operations. Raise the power first, then multiply. So order of operations, do the exponent, then the multiplication. So you've got a problem to work on yourself. Same idea. Pay attention to what you're substituting in, and then when you're ready, resume the video to see the answer. Okay, so in this problem, an initial population of 20 rabbits triples every half year, period. The function f of x equals 20 times 3 to the x power gives the population after x half-year periods. How many rabbits will there be after 3 years? This is understanding. We don't just substitute in 3. The rabbits double after every half year. So in 3 years, that's actually 6 half years. So I would do 20 times 3 to the x, 20 times 3 to the 6th. So I do 3 to the 6th first, which is 729. 729 times 20 is 14,580 rabbits. So this just shows how quickly these functions increase over a short, period of time. And then the final thing is important because I want you to see how these functions change over time. So how to graph an exponential function when you're just given the function. So in these problems, you're going to be able to choose which x values to substitute in. So in this graph, I'm going to choose to use -2, -1, 0, 1, and 2. I usually pick the numbers closest to 0, smallest numbers. They're usually the easiest to substitute. And from here on out, I want you guys to really right now just pause the video again and just evaluate. Get practice evaluating. For an input of -2, what's your output? So do that for these 5 inputs. Find the 5 outputs, and then I'll help you graph the points and create the curve when you're ready. So pause the video, work through the outputs, and then resume it when you're ready to see the outputs. Okay, so you probably got some decimals that repeated. If you rounded them, that's fine. So me graphing this is going to be more of an estimation thing. So when I graph -2, the point -2, 0.06, I'm just going to go for an x value of -2 and a y value that's pretty close to 0, but not quite 0. And then to go to -1, 0.17, I'm going to go to -1 as an x value, go just slightly up, but not by much. The point 0, 0.5, 0, and about, this is 0.5 right here, my bad. Okay, because each tick mark is a half. So if I'm going to 1, 1.5, that would be x value of 1, y value of 1.5, and then the point 2, 4.5, 2, up to 4.5. Now, we're not going to leave these points unconnected. We're going to connect these with a curve. So this curve, best you can, that's kind of the general trend. And this is important. As you go to the left, it's not flat, but it's always getting closer and closer to 0 without ever actually touching 0 as a y value. So that's how an exponential function looks. We would call this exponential growth. And we'll get to that in the next lesson. So, to the last example, just graphing an exponential model of a possible real-life situation. So, this talks about computer mapping software. Allows you to zoom in or out on an area to view it in more detail. The function, 100 times 4 to the x power, models the percent of the original area the map shows after zooming out x times. So you're going to see more of the map after you zoom out. So to graph this function, we're going to pick values that make sense in the context of this problem. In the context of this problem, a negative value for x doesn't make a ton of sense. So I think the numbers that would make most sense to me would be from 0 and just going up by 1. So if I do 4 to the 0 power times 100, that is 100. 4 to the first power is 4. 4 times 100 is 400. 4 to the second power is 16. 16 times 100 is 1600. And you can kind of see the pattern here. We are multiplying by 4 to increase this function. So 6,400, 6,400 times 4, 25,600. So that increases pretty substantially. So to graph this, again, it's estimation. It's not going to be perfect, but it's got to be close to show this exponential trend. So the point 0, 100 is going to be at an x value of 0, fairly close to 0 for the y value. 1 and 400, maybe just a little bit higher, but not by a lot. The point 2, 1600, again, a little bit higher, but not by a ton. The point 3, 6400, well, it's got to be at least above 5,000. At least above 5,000, right? And then the point 4, 25,600, that's going to be way at the very end of the x-axis here, all the way up just above 25,000. So it really takes a huge jump there. So this function is going to look like this if I connect it with the curve and it's best you can. It's not going to be, I'm obviously not very good at drawing, but that's about what the trend looks like in an exponential function. So just getting down the general shape, the pattern, and then next lesson we talk more about the actual real-life applications of exponential functions. We talk about exponential growth and decay. So you should be ready to move on. Please work through the practice slowly so that you're grasping the concepts, because this is a new thing. So you can move on to the next part of the lesson.